In this video, we will discuss the mathematical relationship between pressure and volume for a trapped sample of gas with constant moles and temperature, and how to use that relationship to derive a useful formula. Every year, I start teaching my gases unit by having my students collect data, like this, using probeware technology. As you progress in your chemical career, you will also have need of analyzing larger sets of data. They may not always be this short, so I've made my students graph their data on spreadsheet programs to get used to it, to see if the data makes the shape of a recognizable function, which is something that joyously happens often in nature. Our first graph looks something like this. Now, I don't know about you, but that looks freakishly hyperbolic to me. However, I remember from math class that there is more than one kind of function that can make this sort of shape that's matching our raw data. I'll plot two of these on Desmos so we can compare. Now, if I'm just eyeballing the shapes of these functions, it could really be either one. Check out these two areas I box on the graph. Both of these spots look relatively the same. So what we need to determine whether the pressure and volume behave like a 1 over x graph or a 1 over x squared is to actually graph those functions. So in a spreadsheet program, I'll set up two more data sets with the following patterns. I'll graph one, where I change the volume into 1 divided by the volume versus the pressure. And I'll do the other graph with a 1 over volume squared versus pressure. If either one of our two plots is linear, that would mean that their corresponding equation, well, for our first one, that would look like P is equal to some kind of constant over 1 over V. And for our second one, that would look like P is equal to some kind of constant over V squared. And if our graph is linear, that corresponding equation would be the equation that matches our data. Okay, so here are the plots made from the equations we were just talking about. In this first picture, we can clearly see that this graph is correctly representing our data because we've seen a straight line coming from that equation. Again, this one is plotting 1 divided by volume, and our second graph is 1 divided by volume squared. That one doesn't match as well because we can see it makes something like a y equals square root of x type picture. This means that the pressure value is going to be inversely related to the volume. In other words, as the volume increases, the pressure decreases, and vice versa. Textbooks will often represent this relationship with the following equations. They'll either write pressure is directly proportional to 1 divided by the volume, or they'll write pressure is equal to K, or 1 over volume, or sometimes they'll even say that the product, P times V, is equal to a constant K. For all practical purposes, we can make a new equation that will help us predict new pressures or volumes for a trapped gas if we know some pieces of information about it. Since we know that K will have the same value for a particular trapped amount of gas at a particular temperature, the product, P times V, will always be the same. Therefore, any two sets of pressure and volume conditions will still equal the same K. We can call those pressure 1 times volume 1 occurring at the same moment. That will equal a K. And so will pressure 2 times volume 2 at the same moment. Those two quantities together will multiply to equal K. Using substitution, we can make ourselves a nifty equation commonly found in high school chemistry textbooks. pressure 1 times volume 1 equals pressure 2 times volume 2. And we can use this to predict the pressure or volume of a sample of gas given where we know at least one of the two final quantities. Boyle's law calculations can be pretty simple. Just make sure that your pressure units and your volume units remain consistent throughout your calculations and you'll be set.